All right, good morning, everybody. Morning. I hope everybody had a good weekend. So what we're going to do today is we are going to learn about C++ approaches to doing two things. First, we're going to learn about a keyword called new. And it's C++'s way of using an operator to be able to do memory allocation. And then what we're going to do is we're going to learn about something called class templates. So we've learned about function templates before. And now what we're going to do is we're going to learn about an idea where we want to do certain tasks. And the only difference is that we're going to do the same task over and over again, but the difference is that we want to be able to store different items or use different items to perform this. We would want to use a class template instead of just having to write multiple classes. So in C, we would have to write several structs that do the same thing because we don't have this ability to template. Whereas in C++, we do have the ability to template, so therefore we can do reuse of code. So first, with memory allocation in C, we've learned about this idea of the stack and the heap. And in C, we used a keyword called malloc. And malloc was actually a function, right? And malloc took in a size, a long unsigned integer, and then it multiplied it by a number of elements. So we have a size of integer, size of float, and it allocated a certain amount of memory. Malloc also returned a void pointer, and we learned that we had to cast to a specific type of pointer. For example, if we did a character array, we had to cast a char star because this allowed us to say, all right, this points to a specific location, but I'm going to dictate to the operating system, since C is a procedural language, that this program, that this particular chunk of memory will be interpreted in 8-bit chunks as characters. Does that make sense? So C++ is trying to abstract a lot of this complexity away. So what they're going to do is they're going to use a keyword called new. And this keyword new is going to allow us to be able to allocate memory without having to worry about all of these void pointers and all this nasty stuff. However, because you've learned it in C, you're now going to understand what's going on underneath the hood, which will hopefully allow you to be able to employ the new keyword in a more effective manner. So first, let me show you a very simple example of new. And what we have here is I've allocated a first pointer. So for example, in homework 5, I asked you to pass an integer reference to a function, and then that was the first value read in from the file. And a very common mistake would be that you would allocate a pointer like this, and then pass it to the function, instead of just passing the integer itself. And what ended up happening is this int star only allocates a memory location, not an actual integer itself. Does that make sense? So for those of you who came to my office hours and had made that mistake, you probably remember I told you that what you're doing is you're actually storing the value 0 there, and you're trying to overwrite the very first piece of memory. And that back in the 90s, before you had all these issues, that was actually a federal crime, and that was actually really bad because it was a stack smashing attack. So here, what we're trying to do in C++ is saying, I want to allocate a pointer, but I also want to allocate some memory. If we wanted to do that, there's two different ways. We would just say int star the pointer, and then we'd have to allocate another integer, and then we'd say first pointer equals ampersand x, right? So if the integer is x, then we're now pointing it to the address. The other way is we could go crazy and do malloc, right? It would be 1 times size of int, or just size of int. Here, what we're doing is we're using a new keyword. And what this is doing is it's allocating the pointer and a place for an integer 2. Everybody see that? So it's allocating both. And it's doing all that work in one line of code. So when we use the new keyword here, I'm just saying int, and when I pass 1, what I'm doing is I'm setting that value of that integer equal to 1. So this would be the equivalent of saying int star first pointer, but then I would say int x is equal to 1, and then I'd say first pointer is equal to the address of x. Here I'm cutting out some of the middle work and just saying new int 1, and so that is putting all that together. Does that make sense? So if you were trying to do it this way, then you've created a pointer, and if you passed it the way you were trying to, for those of you who encountered that issue in C, the code would work. So that's one of the reasons why they introduced this new keyword, abstract complexity of void pointers and memory, but also allow us to be able to define that information for us. So, okay, so let me check the chat as well. Does anybody have any questions before I continue? Okay, so what's going on here is we have standard out. And first, I'm just going to print out a message. And if this, okay, there we go. What I'm doing is I'm saying, give me the address of the register. So I have to cast it to void pointer. We're still doing that. And then I'm saying the address here. And then I'm casting the void pointer and saying, give me the value here. And then if I say star first pointer, it's going to give me the value 1. So let me run this, and then I'm going to discuss that delete keyword. So it's going to compile. And we see that we have this register address that's larger because it's an actual register. Here it's pointing at the heap, so it represents only the last few characters in the memory. And then the value pointed to by is 1. Does everybody see that? Yes. Sure. So here first I'm saying, give me the address of the register, right? So I say void star ampersand first pointer. That tells me the register where the pointer is contains its information, right? And then I remove that ampersand, and that gives me the memory location it's pointing to. And then if I dereference it, that gives me the value it's pointing to. So the benefit of using the new keyword here is we don't need to create another register for that specific value. We just have it available. Did I address your question? Any other questions? I'll do the same thing, check the chat. So the next thing I have here, oh, I don't know what that was all about. The next thing that I have here is this delete keyword. So remember how I had malloc and free? In C++, we have new and delete. And so what I'm doing here is I'm deleting memory that was allocated with the new keyword. So the rules that were with malloc and free apply. If you allocate a pointer and you don't use new, then don't call the delete keyword. Just like when we had malloc, when we had a pointer that we didn't allocate with malloc, if you called free on it, it had a huge memory map trace and a segmentation fault. You want to follow that same design paradigm here with new and delete. So in this case, what happened is that it deleted the memory that I allocated here. So this is the kind of the basic fundamental approach to the new keyword. So what I want to show you next is taking this to the next step and using the new keyword to allocate an array. So in the file newarray.cpp, what I have here is I have a long unsigned int malloc size is equal to 5. And then I have a char star new character malloc size, right? So let me fix this. So let me compare what I have in the comment with what's now in the new C++ line of code. So in that comment is the version that you would have to do in C. In C, First, I would call the malloc function. Then I'd have to pass the number of elements. I'd have to pass it as a long unsigned integer because that's the type that we use to represent an amount of memory. And then I have to multiply it by the number of elements and its size, right? So size of char. So we have this, and malloc returns a void pointer. All that's pointing to is just a location in memory. So then we have to cast a char star in order to say that we want this pointer to be interpreted in 8-bit chunks. Then we return the pointer. The new keyword is doing all of this for you underneath the hood. So it's just saying, all right, just give me the number. I will do the times size of for you. Then what I'm going to do is I'm going to do the casting from void star to char star for you. And what that allows us to do is we're doing the exact same task, but a lot of the complexity has been put away. So in C, it's procedural. This line of code that I've commented out is a set of procedures based on our understanding of how computing works in order to be able to give us an array. Whereas in C++, it's treating it like it's an object. I have a number of elements, and I'm going to give you a number of objects. And that pointer is just pointing to that location. Does anybody have any questions about that? So what I'm going to do is I'm going to try to break your brains a little bit here. Because remember, C++ treats things like objects. So notice here that I have standard C out, location of first is ampersand first. So if we were doing this in C++ and I wanted to print the base address of the array, what's the keyword pointer that I would have to put in front of that? Void star, right? So in C++, we're treating things like objects and we want to abstract complexity. So it turns out that we do not need that keyword there. And in fact, let me go back to new int and watch what happens when I do this. When I do this, I'm going to take away those void stars. And if this was in C, our compiler would be crying. But in C++, it's perfectly fine. And it'll do the exact same thing. And so the reason why it's doing that is because C++ is treating things like objects. We're not going full procedural. So we don't need to put void star in front. Now I did this because I wanted to kind of ease you into this idea of why it is that you don't have to. So I'm just throwing that in there along with new keyword. But here in new array, I'm getting the base address of the array just by saying ampersand first. Because in C++ it's saying, hey, we can treat this like an object, and this object has a base address. And so why do I care if it's void star? I don't need the programmer to keep doing all these things. And so next thing, just like before, we have the array operators that allow us to put in the characters. And then I can print out the word. And since I use the new keyword, you see that I'm deleting that array. So what I'm going to do is I'm going to compile it. And run it. And now you're going to see that I'm printing out the location, the base address, and I'm printing out noder there. Yes. Right. In C++. So in C, that is still an absolute requirement because of the procedural nature. So C, its goal is to try to make things work as closely to the computer as possible. So Bjarne Stroustrup felt that limiting people to make procedures was ideologically limiting. So he came up with this idea of C++, where the main design paradigm is trying to treat things as objects and seeing how they interact in the real world. Right? It would be the analogy that I would use here is if I was talking about where somebody lived, like we're all trying to get to my house, right? And I give you my address, and you drive there and you figure out the directions and you get to my house. You don't need to get to my house and then first say, all right, it's made of wood. Okay, now it's got paint. Now it has a certain size. Oh, this is a house, right? That is what's going on with C because it's defining everything procedural. In C++, it's saying, okay, we understand that's a house. That's good enough. Let's access its contents, right? So the drawback with this is if you don't understand what's going on with all this new delete keywords and all these object-oriented approaches such as operators, then it can be very frustrating to try to troubleshoot issues in C++ if you don't understand what's going on. But if now that you understand what's going on with C, now that you understand what a void pointer is, that makes it much easier for you to understand what the new delete keyword are doing and how to troubleshoot what might be going wrong if something shows up. Did that address your question? Oh, are there any other questions? Let me check the chat. Okay, we have a question in the chat. Can you just reiterate why we use new rather than just allocating memory normally? So in C++, they're using a new keyword. So this is, they're even calling it new because it's new as opposed to malloc. And the whole idea is to abstract complexity while from having to type out all this malloc stuff. So all we're doing is say new character array of this size, as opposed to saying, all right, well, I have malloc, I have the size, I have to indicate that the size is times size of character. It returns a void pointer, so I have to cast it to new, to char star. That is the procedural. When I say procedural, what that means is that's exactly what's going on in the computer when we create an array. In C++, because it's treating it as an object, in order for you to be able to actually run the program, all you need is I have an array of characters. And so the whole idea is trying to treat it the way you might actually treat it if you're working on something in the real world. So Kat, does that address your question? You're welcome. Okay, so there's new and delete. Okay, so the next part that I want to go over in lecture today is something called templates. So it ties in nicely with this idea of treating things that we program as objects. So we have learned the benefit of templated functions. Instead of having to write the same function over and over again, I could write one and then use a templated or a generic type to indicate what it is that I wanted to do, right? So now, what if I want to make a class do that? We've learned recently about classes, and then we have private members that we can define as certain types. But what if I want those types to be variable based on a task that I want to do? In C++, we are able to template classes. And just like in functions, we have a template parameter and a generic type that we just go in and say, all right, I want this to be a generic type. And based on how it's templated, when we instantiate the object, so that's called creating the object, the word that you'll see that's synonymous often when you're looking at code is instantiation. So we'll use a template parameter using a generic type, and anywhere where we'd want that generic type to be used, we would just use that generic type instead of making it an actual type. And then what we would do is we would define it as a template when we actually create that object. I'm going to show you how to do that in a little bit. So in the previous lecture, we learned about this void function, and we had this templated function, and we had template class T. The generic type is T. And so the template, when we called it with integer, it would just print out an int and it would overwrite it. Just like so. And here's a crucial thing, because I'm going to discuss something a little later about how we do this in header files that might seem a little counterintuitive, but this is the crucial reason why. When you template it, the code will be written at compile time, which means that it's going to be dependent upon figuring out what your code is trying to fill in. It's not going to be able to compile it by itself. We're going to have to do something a little different than we've normally done. So we have fixed members, we've discussed this idea, and we've already encountered some templates. So when we did a standard vector, and so you did a standard vector of ints and strings, we know that we can template things to certain types. So in your homework assignment, or in the lab, I'm trying to remember which one, we had to do a vector, oh yeah, palindromes. So the one that you did with palindromes, I had you read in several strings, and you created a vector. And you templated that vector to a string. That process where you put it in between the less than and greater than sign is actually dictating the type that I want to store in the vector. I can store integers, I can store strings, I can store characters, I can store whatever I want. I create a class of objects. If you wanted to create several dogs, like we did in the dog class in the lab, you could create a vector of dogs. That is templated. This allows us to be able to do the same kind of task on different objects if we choose. And so the big question is, how can we do this ourselves? So just like a function, what we're going to do is we are going to do a templated parameter at the beginning of a class. There we go. All right, so what I want to do is I want to show you a file a.h. And I want to take you through the basic portions of this to show you how templates work. So in this case, I'm just calling it class A. And at the beginning, what you're going to see is I have a template, and here I have two generic inputs, class T and class U. That means anywhere in the class, or in this case, the variable x is of type T, when it's compiled, it will fill in whatever I choose. So if I just define this as A in X, int and double, it's going to take T and replace every instance of the generic type T with the actual type int, and the same thing with double. Anywhere that has U, double will be replaced. And this is done at compile time. The next thing I want to point out is notice how we have private types, we have the private members, and they are of the generic type. And in the constructor, I have that same thing. You see the generic type in there. Anything that's called inside of that class, the moment I have that there, it can be overwritten, just like we did with the generic function earlier. Anywhere we have T, anywhere we have U, can be overwritten provided it's inside of the class. Yes? Meaning that anywhere, when I call this, and I'm going to show you an example in code in template.cbp in a moment. When I template it, when it's compiled, anywhere that I have these types, T and U, it will be overwritten and a copy will be made in the stack with int and double. It will overwrite them. So these are generic types. Does that make sense? All right, and back. Because that's what I chose in the example. I'm going to show several examples in a moment. Okay? All right, so let me So here is the next important part. And this is that little kind of quirky thing I was alluding to a little earlier in lecture. So what we've learned about in header files this whole semester is that we've split the function declarations into .h and the function definitions into .cpp, right? And this provides us a level of code security. Now, what we are going to learn is that we are going to put all the function definitions into the class in .h in a template class. And the reason why is because it will not compile separate. Because we do not know what the type will be until we actually run the make command. When it's running the make command, it's going to go through the main, it's going to see how we've templated it, and then it's going to make a copy. So therefore, it can't go back and forth between the header and .cpp file. So what you're going to see, and I'm going to show you in a moment here, is that all the function definitions, which are method definitions, in a.h, if I go past here, I'm going to skip that because we're going to cover what those are in a moment. But you see how I have all of them written in the .h file? Does everybody see that? For a templated class, make sure you do that, okay? And I'm going to show you an example first of it working, and then I actually have written up an example where I put them separately, and I'm going to show you that it doesn't compile. So to kind of get to the question that was being asked earlier, in template.cpp, I have a class A. First, I have a const object, and I have cast its templates to character and character. And in this case, one I have the character G, the other I have 72, which is the ASCII value for uppercase H. And then I have the second object, class A, which I have variable B, whereas constructor has 71 and uppercase H. So 71 is the ASCII value for uppercase G. So you're going to see that I'm going to start doing some operators where I do some comparisons here. And then I have a third one, C, where I say 10, and then I cast it to int and float. And then I have 10, and then I have float negative 35.7. So the first thing I would like to show you down here is the friend operator. So the friend operator, because it's inside, I don't need to put in this. I do not need to put t comma u, right? So I have an output, and I have an a value that I'm printing out, and it's printing out in.x and in.y. And what that's allowing me to do is whatever the generic types of the class are, it will print it out because it's a friend. So the first thing I would like to do is I'm going to compile the code. I'm going to show you the first three outputs compared to the inputs. So in template.cpp, the first thing is I'm calling three operators, A, B, and C. And you see I have G, and what's going to happen is it's going to print out as G and H, 10, and negative 35.7. And so there's those three lines of code right there. Does that make sense to everybody? So with this, and this hopefully will address the two questions that were in the back earlier. This allows me to dictate how the class will operate. The next thing that I have is I have an assignment operator equals equals. And what this assignment operator is doing is it's taking that right-hand side and it's const, right? I can compare things that are const versions. So we see that I have a const object, the lowercase, the first variable, right? Lowercase a, that is a const object. So I can compare a const object to a non-const object for equals equals. Since we're not changing anything, this is perfectly fine. So here I say if x is equal to right-hand side x and y is equal to right-hand side y, we return true, otherwise we return false. Now here, does anybody remember what this line of code is doing? All right, well, I will actually, forget I asked that. I will explain what that line of code is doing in a moment. But I'll come back to that. Okay, so here's some of the main code. Let me skip bad version, do not do and do it in the right order, blah, 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 blah. Okay, no. I thought I'd fix this. Okay, so what I would like, forget it. I'm gonna go and describe the code here. All right, so the next thing I would like to describe is what I call the rule of three. So when we have a new and delete keyword, what that's doing is that's freeing memory off of the key. And when we have a class, what this is going to allow me to do is I need to figure out a way to clear off the memory of my own class object, right? So what we're going to do is we're going to be writing our own function called a destructor. And a destructor is a member function that destructs or deletes an object. If we allocated a pointer using the new keyword in the class, we would call delete in the destructor. Otherwise, we leave it alone because the C++ compiler will clean everything up for us. And the destructor is automatically called when the object goes out of scope. So our function ends, the program ends, a block containing the local variable. So if you create a local variable inside a while loop, the moment the while loop is broken, we will call the destructor for that class object. And when the delete is called. So you call delete, you're actually calling the class's destructor. So what I'd like to do is I'd like to show you some rules involving the destructor and how we write it. The destructor doesn't take an argument at all. It starts with a tilde and it doesn't have a return type. And anything that has a pointer or allocated memory, we need to call delete on. Otherwise, we just leave it alone. So what I want to show you here is to go back to this function. And I want to show you this. So we have a tilde, a, and an empty parentheses. It has to be in this order. And we say no pointers, so leave the destructor empty. So right now I don't have anything in there. I don't have any allocated memory. So we're going to leave this alone. So very often when you write your destructor, it will be empty like this, and that's perfectly fine. But if we allocate memory, we're going to see some examples next week where we do that in a lot of detail. You're going to see that we have a need to go back and do deletion. But there's another thing that we want to bear in mind. And that's what this thing we want to bear in mind is what we call the rule of three. So the rule of three is based on years and years of learning from programming mistakes from students, or not just students, but programmers. And the whole idea is how we want to make sure that we do not screw up allocating memory. And what we determined is that if you want to make sure that you account for every possible case where we allocate memory or deallocate memory, there's three methods that we need to write in a class in order for it to be effective. We've learned about the first one, and that's called a destructor. The second one that we're going to learn about is called a copy constructor. And the third one is called an assignment operator. And the idea behind these is that the copy constructor reads in an object and makes a copy of a second object. This would be like if we said int x is equal to y. I'm sorry. I apologize. I literally just described the assignment operator. So if I said a int and float of b, I could actually pass a previously created object to that class member, and that will create a copy of everything. The next one is called the assignment operator. And what the assignment operator does is it creates a new object based on equal. So it's an equals operator. So this would be like int x equals y. Y is still preserved, and then we have a new integer x, correct? The assignment operator there, which is single equals, we're going to define the class, how that works in the method. Hey, does anybody have any questions before I show you code and how that's performed? All right, so let me show you some code, and then we'll dig in and see if we have any more questions. So in this particular class object A, here we have the destructor, right? Empty, we don't have any pointers or allocated memory, so we leave it alone. This one I've now highlighted is called a copy constructor. It brings in a copy of the class, right? And here I call it const, and I call by reference. And here I have a member initialization list because it's a constructor. So x is equal to copy.x and y is equal to copy.y. So you see that? So we have a copy constructor. The assignment operator is a little more tricky. At line 26, so everything I'm about to highlight here, this is what we call the assignment operator. So the first part, we see that like we have in all the other operators, we have operator and whatever we want it to do. So before we had operators equals or less than or greater than, we've done plus and minus, right? Here we're actually doing an equals operator, where if we assigned it, then we have to bring this over. So if this is A is equal to B. And then what we pass in is we pass in an object that I call assign because that is what we are going to assign to the new object. So I call it const, I template it, I have the ampersand there to reduce memory consumption, and we do assign. So now we're going to come to this line of code here. Does anybody have any theory as to what this means? Yes. You're in the right path. You're in the ballpark. So the response is this the calling object, right? So we have a calling object. So if we say x is equal to y, x is calling it, and y is what's being assigned. So this, and to kind of lead in someone to take another guess, let's read the rest of the line of code, and maybe this will help out. This does not equal the address of assign. So what do we think that this is? Yes. Absolutely right. It is the base address of the calling object. So now what I'm doing is I'm saying if the base address of the calling object does not equal the base address of assign. Why do you think we would want to do this? Yes. Absolutely right. Yes. No, the calling object is not assigned, it's the other one. It's if this was A is equal to B, the calling object is A and assign is B. Does that make sense? It is a calling object of whatever the class is. What is your skepticism? A is eventually going to be this. Yeah. Yeah, what we're doing is we're creating a new object and we are going to return it with a call by reference because the calling object is A, but we're going to return a reference on the left-hand side. So, but what you was interesting because that is correct, what you were saying before. If the calling object does not equal the right-hand side's address. So the address of the left does not equal the address of the right. So the whole idea is if I say if A is equal to A, then there's no reason to do all this extra work, correct? I just want to return the address, location, what it's pointing to, and send it off on its merry way, right? If they're not equal, in this case, A is equal to B, then we do the assignment. So this dot X is equal to assign dot X, and this dot Y is equal to assign dot Y. Does that make sense? Okay, so now what I want to do is take us back down here to this equals equals operator. So now what we're doing is we now say that if this right-hand side value that I'm bringing down, if these are equal, that means I'm just saying if A is equal to A, if they're pointing at the same location and they're both the same type, that means they must be equal. So therefore, we're saving ourselves a little bit of work. We are adding a little more efficiency. And as the class types get bigger and bigger, this kind of design methodology becomes more and more beneficial, especially when you're working on, okay, so let me give you an example. So in my data structures course, I have one of the student teams is working with IndyCar. And IndyCar, Matthew Greco is a Notre Dame alumni. He does all the work for getting all those numbers up on the board is who's in the lead and how fast cars are going and all that. And they have sensors all over all these tracks. And so they're collecting millions of pieces of data over the course of a race. And so they have to do things fast and they have to make certain decisions really quickly. And so you get all these pieces of different types of data, you're putting them into class objects and they have to be able to read them fast. So every piece of efficiency and improvement is a benefit to them. So in this case, this is an example of a benefit. If I already know that they're the same address, then there's no reason for me to do a long list of comparisons where I'm just copying it back into itself, right? All right, let me check the chat, see if there are any questions. Okay. Okay, so now that I've discussed new and delete an assignment operator in this keyword, what I would like to do is next go back to where I was hoping to have this here and talk about a couple of common pitfalls. So now we have all the operators, and if I run this, we see that it does the comparison here. And the last thing that I have in this template.cpp code is I call a set X and a set Y method, and then I print it out again. In template bad, I have a.h here. I should have a bad dot underscore h. And what we have here is I have a class that was defined like you learned about it before, right? Where it's separated, and then I have an a bad dot cpp, right? Where I'm trying to do it just like we were doing before. And so if I try to compile it, it really doesn't like this very much. And there's all kinds of things going wrong. And part of the issue is it can't find the comparison because it's on different pages. The reason why is because it defines and fills in all this generic text. I'm going to get back to the question that the questions in the back earlier. It's filling it in after we run the compilation. So therefore, we have to wait. That's why we have to put them all into the same .h file. The other common problem with templates is you have to keep track and make sure that the types match. So here, if I say int float a, and type a, but here it's double and char. If I try saying a equals b, this is not going to compile because they're different types and they can't be compared. Does that make sense? Okay. The next thing, combining concepts, templates, and types of pointers. So if you want to create a pointer to a class object, you use the new keyword. And the way you do it is just like you would do if you were doing an array. You would say the class name, you would have the template type, you would have the star to indicate that it's a pointer. And here, just like before, we did new and then we defined the array, right? We had the type and then we had the length. Here what we're doing is we're calling the constructor for the object. So I'm saying new a int float, and then here I did 10 and negative 35.7. And what that's doing is not just creating a pointer to a class object, it's also allocating all of the memory for me too. Does that make sense? So that's one of the benefits of the new keyword in C++, is it's now more robust so we can apply it to classes. So here, we can use the star C to dereference and call the operator for printing out, right? So now we have created an object and we've created the operator. The user can now use our class simply to create a pointer. They can just call our operator and it prints out easily. Does everybody see that? So now we're tuning it in a way that makes it easier for somebody to use your code. And then we've learned about this dereference as well. Both of those work. So we've learned that star C in parentheses dot is the equivalent of the arrow. And that allows us to be able to do C++ class pointers. So I'm going to skip over all this code. And now what I want to show you here in temp destination is that the main difference here is I've created a pointer, just like I showed you in the code. Here in the slides. Here I have a star. We have to dereference for that to work. Here I've called the assignment operator, and I'm able to do that because I dereference the pointer, and I'm able to set D equal to the information I've allocated on the heap for the object for C. Does everybody see that? So if I dereference it, I can treat it just like I would if these were integers. And then at the end, I call delete C in order to delete that memory because I used the new keyword to do so. Does anybody have any questions on that? Okay, so this is where we're going to start next lecture. There's no way I'm going to get through 5 slides in 1 minute. We'll start there on namespace, on what a namespace is, now to understand classes, and why in industry it's generally considered bad to use what's known as using namespace STD. We'll start there, and then we will continue into more advanced classwork. If there are no more questions, you are dismissed.